Hello everyone. We have made this geometry before. I will attach the link to how to create this type of geometry. And previously we have shared the topology. I've shared the link with you before. If you haven't gone through this, now let's quickly mesh this geometry. We have used fluent meshing for meshing this. We are doing this with polyhedra meshing. Once we are done with polyhedra meshing with hexacore, you can see that the mesh is properly generated. So those of you who haven't know how to do this, you can watch the previous videos. I will attach the link below. So now let's start with the setup for running the simulation of a bioreactor. So first of all, we will add water to the case file since it is not there. Air is the default fluid that is always been there. So for that, you go to the material fluid and double click on air. In that, you will go to Fluent database and look for water liquid. Once you attach it, just copy it into this. Now you can see there is air and water both present in your fluid material. Once we have successfully added water into the fluid material, go to multi-zone and select eulerian mode for calculation. Water phase is our primary phase and air will be our secondary phase. So once you set up the primary and secondary phase, then you set up you put a bubble diameter of 3.5 mm, which we have calculated before. Once you set up those, let's set up the phase interaction. In this we are using Siller Newman and we are just using substitution only 0.072, and the water phase and air phase will be a interfacial area symmetry. You will not use any population balance over here. For viscous model, we will use standard K epsilon with dispersed phase calculation, or you can also use per phase. Now since we have already set up all this, now set up the gravity direction. Since our direction is along z and the gravitation will act along the negative z direction, we'll put minus 9.8. Now we have to separate the cell, separate the single layer of cell at the inlet. To do that, create a second boundary layer at the inlet surface of a single cell layer. Once you create that cell layer, separate it from the fluid zone. This will help you to do your calculation more accurately, because in reality when you do you are sparging air from the inlet surface, there is a thin layer of air that will be 100% pure air. So for our calculation, those single layer will not be calculated. This will give us a better accurate calculation. Once you successfully separate this, you can see there are 5 zones over there in our cell zones. One of those is our inlet surface zone. We'll name it as source and we'll keep different condition for that. After successfully separating our inlet surface zone, we will do the you will set up the inlet and outlet boundary conditions and wall setup. For inlet, we'll only put for air phase air velocity of 0.01 meter per second. We have calculated, and the volume fraction should be kept as 1 because we are not injecting any water from that point. And the outlet should be pressure outlet, and in case of backflow, put backflow is equals to volume fraction 1 for air, because in backflow we don't want any water to come back into the reactor. For cell zone, we are putting 300 rpm at the rotating speed. For rotating fluid zone 1 and rotating fluid zone 2, where due to the motion of these two fluid zones, the momentum will be transferred to the entire body of the liquid of the reactor. Once you said that, we will also put are rotating shaft at 300 rpm, so that the shaft will also move with the rotating fluids. It is important that our axis of rotation should along z axis. We'll keep that as 1 because it is a standard common practice in ANSYS that our rotation of axis should, is along z axis. But in case you have drawn it along x or y axis, so you should always keep that axis value as 1, or you can change the axis value as per your requirement. If it is at in 45 degree, you should always mention those coordinates over there. Once it's done, you just initialize your Fluent case. Now we will patch air onto the air body. So for that you will just go to patch and put select air and volume fraction as 1 in the air body. Once initialization is complete, we will create a separate plane to see the volume fraction, and we will record the volume fraction over that plane to check the contours of volume fraction with our simulation time. You can see here we have successfully generated a plane. Here red is air, here red is water, and blue is water. Now we have changed, air is at red at the top and water is blue at the bottom. So that's what we need. As the air increases sparged from the bottom, we'll see how the contour is changing. We are doing steady state calculation. We have initially put 1000 iterations, and we are recording. This is how we record the contour with every iteration. We'll save it in PNG format. So let's record and save it for calculation. You can see our simulation has been started. Now our simulation has started properly. We can let it run until it reaches to conversion. You can see there is a small changes at the upper surface of the water. Slowly it will change as the momentum is transferred. We'll let it run for some time until it converges. If it doesn't converge within 1000 iteration, we'll increase the number of iteration and let it run. Now to see the results, how our profile changes and how it reaches to conversion, please like, share and subscribe to my channel. And in future we will see how different phase interaction drag coefficient affects a fluid.